Okay. So first of all, when you build a physical model, you usually do so by assuming reasonably assuming physical assumptions, and these assumptions are usually valid on a limited range of scales. So ideally, what you would like to do is you would like to use such a model as the basis for a simulation, but that's unfortunately very often not possible. I will come up with a little example that motivated our studies in a second. So if you look at, let's say, only the representation of a function that involves a wide range of scales, what you see is that the numbers of unknowns that you need in order to represent it in a computer is, let's say, O of epsilon to the minus d, where these that I mentioned, and epsilon is the smallest resolved scale, or the smallest scale apparent in your data. So if epsilon is very small, that means you will have to involve a large number of degrees of freedom in your numerical model. And the number of flops, basically, that you need is usually not smaller. Because you need to process at least every degree of freedom once. So the problem that mainly motivated our studies is climate simulations. So climate simulations are among the most horrible problems that you can encounter in simulations. So you have basically every climate simulation consists of, if you can break it down to two parts. So there is the dynamical core on the one side. The dynamical core is responsible for the discretization of all the dynamical equations like prognostic and diagnostic variables such as pressure, velocities, temperature, and so on. And everything that you cannot resolve on this dynamical core that usually works on a core scale of order capital of H, I don't know if you can see that from the back of the room, everything that you cannot resolve is put into so-called parametrizations. So these are inherently subscale processes that somehow enter quantities that live on the dynamical core. And these two scales, the resolved on the left and the non-resolved, they have to talk to each other somehow. So now, if you want to project data from the dynamical core, from the core scales onto the fine scales, that's actually the easy problem. And so the only thing you can do if you want to go from core scales to fine scales is you interpolate, unless you have more prior knowledge. The interesting question, or more difficult question, is suppose I have a bunch of fine scale information. What fine scale information is relevant on the core scales? And that's called the upscaling problem. Okay, so just a couple of more words about climate systems. So they're inherently multiscale. They're transient. What makes it in particular difficult is they are dominated by advection. Okay, so how's the scale coupling done? Unfortunately, in many cases, only heuristically. So I'll come up with an example in a second. So what we need is actually consistent numerics that couples these different, or couples processes that live on different scales. So how do we simulate the effective behavior correctly? So I promised an example. If you think of sea ice, usually there are climate models, usually have an ocean component, atmospheric component, and there is an interface between them. That's a sea ice model. And what is often done is that the sea ice model, suppose you have a grid cell and paleoclimate simulation that could be like edge length of 200 kilometers, which is quite large. What the sea ice model would do is it would compute an average distribution of the sea ice and give this information handed over to the dynamical core. So you average and pass this information on the core scales. So what's wrong with that? Little example. So what could we do? Or one possible solution is I have a model that involves small scales. Maybe I can find an effective model that basically describes the limit of my dynamics if the scale separation becomes large. So that's called an effective model. Okay, let's come up with a very simple example and see what averaging does. So that's I think the most simple example that you can think of. It's an a diffusion equation, stationary, with a diffusion term that involves scales of the order of epsilon. Let's say on an interval 1D. So what is the effective equation? I could just average this A and try to solve this equation. So is it that? Let's see. Okay, I'm not going to go into that bunch of mathematical arguments, yada, yada, yada. So the effective equation of this one is, or the effective coefficient is given by the inverse of the harmonic average. So that's quite counterintuitive. And what you have is that the arithmetic average that I proposed, that we might have guessed is the effective coefficient, is usually much larger. That means you diffuse too much. Okay, so then why not looking at homogenized equations for climate models? Okay, first of all, that's, in general, you don't have a scale separation. That's problem number one. Next problem is advection problems are often inherently hard, and besides, homogenization is very technical. And so what you're left with is eventually, and if you don't have an effective equation, you have a large range of scales. So this epsilon is basically much smaller than 1. So what you could do to come up with an effective numerical simulation is you have to do some micro-scale computations only locally. That's the only option that you have. So these homogenization principles that we just saw should be reflected by numerical methods. So for elliptic problems, this is kind of easy. Okay, let me skip that. So let's start using, there is a bunch of methods out there. There's numerical multiscale methods, HMM methods, multiscale Eulerian Lagrangian adjoint methods, variational multiscale methods, and so on. We focus on, in this talk, on multiscale finite elements, but what I'm going to present to you is not tied to multiscale finite elements as long as you obey some certain localization principles that is basically inherent to the physics of the problem. These methods are known from porous media and oil reservoir modeling. And they're out since approximately 20 years. Okay, so what's the basic idea? Suppose I have an equation like that. That's a stationary diffusion equation with oscillatory coefficient, oscillatory diffusivity. If you start to tackle this problem with a standard finite element model, in the simplest case, you would use these head functions as a basis. So what multiscale finite elements do is they compute basis functions or pre-compute basis functions in each cell. In each cell in the 1D, you have, in the 1D problem, you have 2 basis functions in the standard setting. And you use the boundary values of these and solve this problem locally and add this as a corrector to your basis function. Okay, so what you end up with then is a method that allows estimates like that. So H is your core scale. U0 is in the solution of the effective problem. For this kind of problem, you know the homogenized problem. So it basically tells you that if you resolve all the fine-scale oscillations, you end up with a method that looks like a finite element method, a standard finite element. If you don't, you approximate the average correctly. That's the point. So, okay, so our model problem is slightly more complicated. We want to have, we want to simulate an advection diffusion equation that allows coefficients on several scales. First of all, this velocity, this background velocity could have resolved or non-resolved scales. And this term is probably coming from imagine some parametrization of subgrid processes. We want the Peclet number to be high. Peclet number is something like Reynolds number for flow problems. So it tells you how dominant is the advection. So the C can basically come from, I don't know, two-phase Darcy flow or from some climate, some discretization of a climate, of a fluid problem. Okay, so yeah, if we apply these methods naively and pre-compute basis functions as in the standard finite element settings, you have to solve an ODE, and you see, okay, that doesn't work. So you pre-compute the basis functions in each cell by setting certain boundary conditions. But unfortunately, what you see is that if your advective terms are dominating, that these basis functions develop boundary layers that do not reflect anything of the physics that you would like to simulate, and that's the problem. So the localization principle that respects advection looks different. Namely, what we suggest to do is we suggest to track characteristics or of the flow on the core scale and do something not really fully Lagrangian on the fine scale. I'm not going to elaborate. I won't have time to go into what we do in the fine scales, but on the core scale, you want to make essentially advection invisible. Okay, so first problem, first example, if you do that, what you see here is a comparison of a high-resolution FEM model. So that the solution you see in black. Red is a standard finite element solution with 10 elements that's supposed to represent the coarse model in a standard setting, and the multiscale finite element in green. So if you have, so what you see is that the standard finite element starts to developing phase errors. And besides, it does not capture the effective behavior, also not on the subgrid scale. While the multiscale finite element solution that has boundary conditions on the characteristics of the flow actually does. Okay, nice thing. Unfortunately, well, nice thing because you can pre-compute the basis functions in parallel for each cell. So that's, with this respect, the method scales with a number of coarse cells. That's actually quite nice. Unfortunately, the applicability of this method is quite limited, but it helps to understand what you have to do correctly. Okay, so if you want to overcome the difficulties that are connected to fully Lagrangian methods on the coarse scale, maybe we can do something semi-Lagrangian. Semi-Lagrangian means you do essentially something Lagrangian backwards in time, but only locally in time. So how do we keep track of information in the basis function? Because that depends on the entire domain of dependence, and this domain of dependence might grow in time. So there is some memory that these basis functions must have, and maybe we can reconstruct them. And next question is how to design a coarse global problem. Okay. The method that we now propose, or actually it's the basis for a framework of methods, has essentially 4 ingredients. First of all, we take a coarse cell. On this coarse cell, there is a fine scale mesh. You trace it back in time. You try to use information from the previous time step and reconstruct a set of basis functions, evolve it with certain boundary conditions, use it as a global, use these bases for your global problem, and do one cheap global step in time. So, how much time do you have?
Like 5 meetings or something like that.
Okay, that's cool. Thank you. So you look at, let's say, your coarse mesh, you look at one cell, and what you do with this cell is you trace it back in time. On this cell, and at time tn, in which you don't know your solution yet, that's the time step that you want to make, that you want to get information from. That's your next time step, basically. You don't know the basis, and you don't know the solution, of course. So you don't know the weights of the basis function. But what you can do is you can trace back the cell in time. What you get is a distorted cell. Let's call it k tilde at time tn minus 1. What you know at time tn minus 1 is your solution from the previous time step, right? What you don't know is a basis on this distorted mesh. By assuming certain things on this basis, we can maybe reconstruct reconstruct this basis by if we knew these weights. So if you do it in a conformal setting, you can come up with a reconstruction of a basis function like that. You solve an inverse problem on each of these distorted cells. This un minus 1, you know, that's the solution from the previous time step. You just have to evaluate it on this distorted mesh. Here is your representation that you want to be in some sense close to this solution. You want it to be optimal. So you optimize this functional with respect to, let's say, in this setting, 3 unknown basis functions. And here you have a regularizer. Essentially, with a regularizer, you can be a bit creative. Depends on your setting. What average do you want to? Are you interested in? Also here with the optimization, in what space do you want to have this average? Are you interested more in averages for the derivative? I think if you're an engineer, you might be interested more often in stresses when do structures fail, rather than in L2 averages or so, like displacements. Okay, so you solve this inverse problem, and you have essentially then constructed a basis on the distorted cell in the previous time step. So what do you do with that? Well, the next thing you do, you need to construct a basis at your original cell, the non-distorted one, at the next time step. So what you have to do then is you have to evolve these basis functions to the next time step, but keep in mind that we're in a Lagrangian setting. So if you have a conservative problem and the background velocity is not solenoidal, means it has a divergence, you have to take into account another term, you have to set appropriate boundary conditions, and you evolve the problem to the next time step, and your end state is the basis function that you're hopefully looking for. Okay, so let's see how this performs on a simple 1D problem. So we have a conservative equation. Background velocity is not constant, so it has a divergence in 1D. Pretty oscillatory background diffusivity, and resolved and non-resolved background velocity. So that's kind of a hard problem, and the method that I presented to you before would not be able to tackle that. Blue is multiscale finite element solution, red is standard solution, and black is the reference solution. You almost see no difference between the blue and the multiscale finite element and the standard solution, the reference solution. 10 elements only, and pretty horrible background velocity, and quite oscillatory diffusivity. Okay, another time step of this. So what are the features of this method? First of all, it's embarrassingly parallel because you can do this reconstruction in parallel. So essentially, you have to do it in each time step, but what you have to do in each time step essentially scales with the number of coarse cells that you have. You can design, I used an implicit method for the time stepping, but you can design an explicit method as well. And the idea, as I said, is quite generic. It's not limited to FEM. You could come up with discontinuous Galerkin style discretizations. Another question would be, what are the effective fluxes between coarse scales then? But anyway, you can generalize it to ND. Here you see an example of such a modified head basis function. And yeah, let's look at a 2D example. Unit square periodic boundary conditions, and again, pretty horrible coefficients. Peclet number is around 10 to the 6th, which is pretty high. Okay, what you see on the left side is the reference solution. Let me start the simulation and hope that it works. Upper left is reference solution, lower right is standard finite element solution, and upper right is the multiscale solution that we propose. Here on the left, you can see the background velocity field. It has a divergence. The problem is conservative, and that's the diffusivity. I don't know if you can see that, but there are lots of heterogeneities inside. So let's start the simulation, and nothing happens. Great. Okay, I never got sabotaged by computers so much as today. Yeah, I would have loved you to see that, but let me explain you what you were supposed to see. Reference solution looks nice, pretty oscillatory. This one should be very, very close to the reference solution, while the non-multiscale solution essentially, after some time, does not have to do anything with the reference solution anymore. I really apologize for the technical problems that we had. Just few remarks, problems on the data list, on the bucket list. The Semi-Lagrangian multiscale method is designed in such a way that it has the natural capability of assimilating data, but not into the solution, into the basis. So that's something we're chasing right now. I would like to combine these ideas with multiscale vector elements. I won't have time to go into that, but you can essentially come up with multiscale methods in different spaces like hcurl, hdiv. That was basically an H1 conformal method I presented to you. Conservative problems, and we have a PhD student working, starting to work on the simulation of urban climate, like tracer gases that that basically evolve in cities under external flow. Okay. Again, apologies for the problems. Thank you for your attention. Yeah, I'd like to stop here.